Okay, yeah, thank you for having me. I've come to rather enjoy these online seminars where we can see people from far away that it's not so easy to see. I think I was invited to give a colloquium talk. So anyway, so I hope I haven't been to this seminar. I don't know the culture exactly, but I hope it will be broadly understandable. And please stop and ask questions. You can unmute yourself or put things in the chat if you have questions or thoughts. Okay, so this talk is about the relationship between the Lipschitz constant of maps and topology of maps. So we have two Riemannian manifolds and we have a map between them. And the geometric feature of the map we'll pay attention to is the Lipschitz constant, which I'll remind you what that means in a second. And the topological feature is the homotopy type of the map. And I'm curious about how they are related to each other. Okay, so let me remind everybody what is a Lipschitz constant. If I have a map between Riemannian manifolds, we say the Lipschitz constant is at most L if for every curve in the domain, the mapping stretches the length of the curve by at most a factor of L. So the length of the image is at most L times bigger than the length of the original curve. You can also describe it in terms of the derivative. So if the map is C1, then the Lipschitz constant is at most L if the norm of the derivative is at most L at every point. In other words, the derivative stretches the length of vectors by at most a factor of L. Okay. And for all the things we'll talk about, it's fine to imagine that our maps are smooth. So you can have that in mind if you like. So that's the Lipschitz constant. And then the question again is, how is that geometric feature of the map related to its homotopy type? And in the first part, I will survey what we know about this question. And in the second part, I'll discuss some of the methods, especially of recent stuff. Okay, so let's start by thinking about maps, the degrees of maps between spheres. So Sn will be the unit n sphere. Suppose that we have a map from the unit n sphere to itself with Lipschitz constant at most L. How big could its degree be? There is an upper bound that it's at most the Lipschitz constant to the power n. And I'll sketch the proof of that for you later. And there's an example that shows that that's roughly tight. So there are examples where the degree is at most a dimensional constant times the Lipschitz constant to the n. So up to a constant factor, those match. Another example is the Hopinvariant of maps. So suppose we have a map from S3 to S2, which has Lipschitz constant at most L. How big could its Hopinvariant be? Misha studied this in the 70s, and he showed that it's something like Lipschitz constant to the fourth. So it's at most Lipschitz constant to the fourth, and there are examples which have Hopinvariant at least a constant Lipschitz to the fourth. So up to a constant factor, the answer to this scales like Lipschitz constant to the fourth. Okay. So the state of the fields in the 70s was that there was a general theory that gave upper bounds for all the rational homotopy invariants of Lipschitz maps. And in a few cases, like the ones we just looked at, there were constructions that basically matched the upper bounds, say up to a constant factor. But for most cases, there was actually a substantial gap between the constructions and the upper bounds. And I'll show you some examples in a little while. And then after that, there was not much progress until recently, until the last 5 or 10 years on these questions. The progress started with a related problem called the Lipschitz extension problem. So suppose now that I have a map from a sphere to another sphere, which is contractible, and it has Lipschitz constant at most L. So it's contractible. That means it's possible to extend little f to a map big F that maps the ball to the sphere. And the question is, what does the Lipschitz constant of the extension need to be? So what function of L can we put here so that we're guaranteed that we can build an extension with Lipschitz constant at most L? So maybe it's good to mention that you can think of the Lipschitz constant as one way of describing the complexity of the map F. If you start with a map F like this with Lipschitz constant L, then you can approximate it by a simplicial map that involves like about L to the n, L to the m, I guess, simplices, which is another way you might measure the complexity of the map. So this question is asking, if we have a contractible map with some complexity, how complicated do you need to make the contraction of the contractible map? I think it's a very natural question. There's a soft argument that you can put some function of L here, and it's just because the space of all the L Lipschitz maps from Sm to Sn is compact, and the subset of the ones that are contractible is a compact subset. And so by compactness and continuity, you can put something here, but that's a non-constructive argument. And in the 90s, Misha sketched a proof with an explicit thing here. And the explicit thing here is a tower of exponentials. So it looks like this, more or less like this. And the height of this tower is at least roughly m minus n, the difference in the dimension of the spheres. Okay, so it's explicit, but it's kind of huge. And I wondered about this. I made no progress. I couldn't figure out how to get started. And so I was very impressed when like a basically complete answer to this question appeared over the last 5 to 10 years. So this theorem is work of Chambers, Dodderer, Manin, and Weinberger, and then also Berdnikov and Manin. So it says for every pair of dimensions, there's a constant, so that if you have a contractible map from Sm to Sn, then you can make a contraction, and the Lipschitz constant of the contraction is only a constant factor times bigger than the Lipschitz constant of the original map. This is a huge improvement over the previous bound with the tower of exponentials. It's sharp because, well, this couldn't possibly be smaller than this. So it's sharp up to a constant factor. And the constructions and the idea of the constructions are neat. And these techniques open the door to some further developments. Okay, so I wrote a survey article at some point about this theorem and its proof and background. And you can find it, if anyone is interested, you can find it on my webpage. Okay, and so the ideas and techniques of this led to some further improvements on the questions I was talking about at the beginning. So I mentioned that after the 70s, for a lot of problems that we were talking about, there's a gap between the constructions and the upper bounds. Okay, so remember that for maps from Sn to itself, the degree is bounded by the Lipschitz constant to the n, and that one is sharp up to a constant factor. But what if we replace the n sphere by other manifolds? Well, for any manifold, we still have this bound that the degree is bounded by the Lipschitz constant to the n. I'll show you the proof in a little while. It doesn't depend on what manifold it is. But when is that sharp? Okay, so the simplest manifold that wasn't understood by the old methods is in 4 dimensions. The reason for that is that if your manifold has a big fundamental group, then you can use that to figure out stuff about this question. And there's a story there, but it's not as exciting, I think, as what we know in the simply connected case. So then if you'd like to find a simply connected manifold, which is not a sphere, then to get interesting examples, we have to start in dimension 4. And the first tricky one, that really requires new ideas, is something like this. Take S2 cross S2, connect some with itself. So we take a Lipschitz map from this manifold to itself. We always know the degree would be bounded by the Lipschitz constant to the 4th. And if you play around with simple constructions, it's not too hard to find an example where the degree goes like the Lipschitz constant cubed. And that gap was there for a long time. I don't know if anyone exactly wrote this down, but this is not that hard. But then this gap here is interesting. Okay, so that gap was figured out by Sasha Berdnikov and Fedor Manin. And they constructed tricky maps from this manifold to itself that are L Lipschitz, and they actually have degree on the order of L to the 4th. And then they wondered, what would happen if we connect some more copies of S2 cross S2? And they thought about that. And they figured out that, so let's say M sub k is take S2 cross S2 and connect it with itself k times. if K is 2 or 3, then we can make L Lipschitz maps with degree on the order of L to the 4th. But if K is at least 4, then there's a transition, and then the degree is little o of L to the 4th. And this little o of L to the 4th, I worked with Sasha and Fedor, and we figured out more quantitatively what's going on there. Not totally precisely, but we have these upper and lower bounds. If K is bigger than 4, and you look at a map from MK to itself that's L Lipschitz, then the degree is at most L to the 4th over log of L to the half. And that upper bound is in the right ballpark in the sense that we can construct maps where the degree is L to the 4th over log of L to the 4th. Okay. Maybe I should say that these are some very particular manifolds, but this is a reasonably general story, and these are the simplest manifolds that illustrate the story. So it's not quite true. Yeah, so trying to say the general thing is a little bit complicated, and we don't have matching upper and lower bounds for everything you might hope for. But for a lot of manifolds and maps and situations, we have reasonably good upper and lower bounds of this kind. Okay. So I was very surprised when Sasha...
But this exactly which doesn't follow from minimal model.
What's that?
It doesn't follow this estimate. The bound and degree doesn't follow from minimal model argument, right?
The proof of this still involves minimal models, but it involves more than the minimal model argument from the 70s.
Okay, so there is some more general theorem with minimal models, or finite theorem, right?
Yeah.
Okay.
Okay. Okay. So that's an overview of what we know about this question, and then in the next part of the talk, I'll try to explain how we know these things. Oh, and I just wanted to say I was very surprised when Sasha and Fedor explained this to me. So first of all, I was kind of surprised by this, that there was this clever map that they explained to me. And once I saw the clever map for K equals 2, then I thought that that there would be maps of degree L to the 4th for almost any manifold, as long as it had high degree maps to itself. And so then I was even more surprised that there was this transition between 3 and 4. Okay, so we're going to try to build up to talking about what these maps are like and giving at least a hint of what causes this transition and maybe how a proof of a bound like this goes. All right, so let's start to talk about some proof ideas, and we'll start at with the most fundamental thing. If we have a map from a manifold to itself, why is the degree bounded by the Lipschitz constant to the n? So here's a sketch. Suppose I have a map from M to itself. It covers each generic point in the target at least norm of degree f times. We can assume that this map is smooth without loss of generality, and then can use Sarge's theorem to have generic values and Brouwer's definition of the degree. So almost every point in the target gets covered this many times. Therefore, if you look at the volume of the image and you count it with multiplicity, then it's the degree times bigger than the original volume. Or it's the degree of f times bigger than the volume of the target, I should say. Okay. On the other hand, it's not hard to see how the Lipschitz constant controls how volumes stretch. So in general, if you have a k-dimensional submanifold of M, then its volume will stretch by at most a factor of L to the k, because the lengths stretch by at most a factor of L in each direction. And so in particular, this sigma k could be itself M. So the volume of the image of M is at most the Lipschitz constant to the n times the volume. And that's true with multiplicity. And if you compare this and this, then you see that the degree is at most the Lipschitz constant to the n. Okay. So for degrees of maps between manifolds, at least for the kind of manifolds that we were looking at, this was the only available bound until recently. Okay, now let's start to talk about mappings. So for maps from the unit sphere to itself, there's an L Lipschitz map whose degree is on the order of L to the n. Here's what it looks like. So here's my domain and here's my target. And inside of the domain, I pack a bunch of small balls. These balls have radius 10 over L. L is the Lipschitz constant. And the number of balls that fit in here of that radius is on the order of L to the n. Then what I do is I take each of these balls and I wrap it over the whole sphere. I stick a base point on the sphere. Here's my base point, star. And I take, say, this ball here, and I wrap that ball around the whole sphere, and I map the boundary of the ball onto the base point. And with a radius of 10 over L and an L Lipschitz map, I can stretch that out to a ball of radius 10, which is big enough to cover the sphere. Okay, and then since then what I do is I map the complement of these balls just to the base point, and that's continuous because the boundary of every ball already went to the base point, so it fits together. Okay, and then the degree of the map is the number of these balls, which is around L to the n. So that's what the map looks like. Now we're going to try to visualize some more complicated maps. So a way that I've found helpful of explaining these later, more complicated maps is to think about the preimages of stuff. So for the map we just described, I'm going to take on this side a unit ball, a blue unit ball in the target. And on this side, I'm going to draw the preimage of that blue unit ball, which are a bunch of small balls. Each of these small balls has radius 1 over L, which is the radius it needs so that after we stretch it by a factor of L, it can cover that. Okay, so this picture describes, it gives a decent sense of the mapping that we constructed on the last slide. Then at the end, we would have to say, how do we map the outside of the leftover white region here onto the leftover white region there? It takes a little bit of work, but it's not super hard. But this is very visual, and it will be able to use that to get some sense of some more complicated mappings. Okay. So let's go to this theorem of Sasha and Fedor. Yeah, I mean, maybe also worth saying. I wanted to be a colloquium style talk, so I tried to give sort of an overview. And there are 2 or 3 ideas for constructing tricky mappings that have a big rational homotopy invariant and a small Lipschitz constant. And I think this one is the neatest. I couldn't put all of them in the talk, so I picked one. I tried to do one in depth to give a flavor of the kinds of things people are doing. Okay, so I'm going to try to give you a sense of what this map is like. And by looking at that map, it's also going to give us a hint about why there might be a change when k goes from 3 to 4. All right. So we're going to try to make a map from M2 to itself. So first, let's visualize M2. So M2, remember, is S2 cross S2 connects some with itself. It's a 4 manifold, but I tried to draw it here. So in this picture, this side is S2 cross S2. And this side is S2 cross S2, and we've connect summed them along here. And in blue, I drew a tubular neighborhood of this S2 and that S2, and those two spheres intersect at this point. And in green, I did the same thing for those 2 spheres. So this thing that looks like a blue circle is really a blue 2 sphere. That's a blue 2 sphere. That's a green 2 sphere. And that's a green 2 sphere. And I took tubular neighborhoods of all of them. Okay. And then this yellow thing is just a curve, tubular neighborhood of a curve that goes from the intersection point of these 2 spheres to the intersection point of those 2 spheres. Okay. So sort of the significance of those things is that this is like a fairly simple cell structure on this manifold. It has 2 0 cells, a 1 cell, some 2 cells, and then the leftover white stuff is a 4 cell. And I took each of those cells and I thickened them, because the thickened versions are a little bit better for thinking about the geometry of mappings. So each of these two spheres has radius around 1, and it has thickness also around 1. I know it looks a little bit thin in the picture, but it was hard to draw it otherwise. But around 1 just means all of these things are fixed. They don't depend on our mapping. It has some thickness, so it's around 1. Okay, so that's how I want to visualize my target. And then to visualize my mapping, I'm going to try to picture the preimage of the blue stuff, the preimage of the yellow stuff, the preimage of the green stuff. Okay, so let's start by trying to imagine the preimage of the blue stuff here, of this 2-sphere and that 2-sphere. The preimage is going to, so first of all, now I'm going to start to draw the domain. The domain is also a copy of M2 that has some topology, but the topology of M2 isn't actually super relevant for this. And so to get the stuff I care about in the picture, I'm just going to draw a ball, like a typical ball in M2. And I'm going to draw what the preimages look like inside that ball. Okay. So here's my domain. All right, so the preimage of this blue thing looks sort of like a grid. And in this grid, each of these horizontal lines represents a two-plane, a tubular neighborhood of a two-plane. And each of these vertical lines also represents a tubular neighborhood of a two-plane. And each of these intersections, each of these crossings represents just a little ball. And these little balls get mapped onto that crossing. So each of these crossings gets mapped onto that crossing. And these horizontal two planes get mapped around this 2-sphere many times, because each one of those goes there. And the vertical two planes get wrapped around that 2-sphere many times. Okay, so these are tubular neighborhoods of a two-plane, and they have a small thickness, 1 over L. And that 1 over L comes because then when we stretch it by a factor of L, it's now as thick as this tubular neighborhood here. And maybe I'll put that in the picture. So this little thickness there is 1 over L, and then it stretches. That little thickness there is 1 over L. It stretches by a factor of L, and it gets mapped there where it has length 1. Okay. There are L squared horizontal two planes and L squared vertical two planes. And so there are L to the 4th crossings. And each of those crossings represents a little ball of radius 1 over L. There are L to the 4th balls. Each one of these balls gets mapped there, and that's my degree of L to the 4th. Okay, let me pause there and see if there are any questions about this picture, about how this thing maps to that thing. Okay, good. Okay, so next I'm going to try to figure out what the preimage of the green stuff looks like. And the first, I'm going to try to figure out what the preimage of the green stuff looks like. And the first idea that occurred to me is to do the same thing. So I make, on one half of the domain, I have this blue thing. On the other half of the domain, I have this green thing, which is just another copy of the blue thing. This green thing maps to that green thing, just the same way that blue thing mapped to that blue thing. And they're like on opposite, and they're on different halves of the domain. So there's like even a little space between them, and you could imagine this space is around 1. Okay, and it turns out that that idea does not work. The problem is we have to figure out where to put these yellow tubes. So there needs to be a yellow tube from each one of these crossings to one of those crossings. So this one could go to any of them. It's not so clear which one should go to which one, but there should be a yellow tube there. There should be a yellow tube there, and so on. And the problem is that there's not enough room for all these yellow tubes. All right, so let's think about how big they are and how many there are. Well, because our degree is L to the fourth, there are L to the fourth of these crossings, and each one has a yellow tube. So there should be L to the fourth yellow tubes. These yellow tubes have a radius of L, or thickness, if you like, of L inverse, because after they get stretched by a factor of L, they have to go over that yellow tube, which has thickness 1. Okay, and in this plan, where I put the green stuff separated from the blue stuff, each of these tubes has to go a length 1 to get from blue land to green land. And now they don't fit. I have L to the fourth tubes. They have a thickness of L inverse. So their volume would be L inverse cubed times a length of 1. So the total volume of all this stuff is L, which is much, L is going to infinity and the volume of my domain is constant, so they don't fit. Okay, so the problem that came about here is that it was not a great idea to put this vertex way on the other side of M from that vertex, because that forced this yellow tube to be long. I would like to put this vertex right next to that vertex so that I could have a short yellow tube from here to here. Then this length would be only maybe 1 over L, and my yellow tubes would fit. So a better plan is we would like to kind of move this green stuff over in the blue stuff and interweave them. So there's a blue lattice that looks just like before. There's a green lattice that looks basically similar to it, and they're somehow interwoven so that each vertex is right next to, each blue vertex is right next to a green vertex. And then I stick my yellow tubes to connect neighboring vertices. Okay. But there's a new problem in trying to make this picture work. Why don't I pause there?
Yeah, but they seem to intersect, yeah, because it's two-dimensional object and in four manifolds, so they tend to intersect, right?
Yes, right. Okay, so that's the new problem. Yeah. So this green thing represents a 2-plane. This blue thing represents a 2-plane. We're in a 4-manifold. So generically, it seems like they should intersect. And that's a problem because they're not allowed to intersect. Since the blue set is disjoint from the green set, their preimages have to be disjoint. So we have a new issue when we try to put them on top of each other. How do we make sure that the green 2 planes are disjoint from the blue 2 planes? Okay, so here's how we do it. So let's put all these planes in coordinates to help us figure out how they intersect with each other. So the vertical blue lines here are going to be 2 planes in the x1, x2 direction. And the horizontal blue lines will be 2 planes in the x3, x4 direction. So each one of these 2 planes will intersect each one of those 2 planes, which is supposed to happen. Those are all these blue crossings. That's no problem. Now, let's put the green 2 planes. So the vertical green 2 planes in coordinates are going to be in the x1, x3 direction. And the horizontal green 2 planes will be in the x2, x4 direction. Why does this help? So I need to know, for example, that these vertical blue 2 planes do not intersect these vertical green 2 planes. And if I have a 2-plane in the x1, x2 direction and a 2-plane in the x1, x3 direction, generically, they don't intersect. If they did intersect, they would intersect in a whole line in the x1 direction. But if you translate them each generically, they won't intersect at all. And the same thing holds for each pair. So the x1, the blue x1, x2, let me color code. So blue, blue, green, green. Okay, so if I pick any pair where one is blue and one is green, say this one and that one, those 2 directions both have an x4. And that means generically, these 2 planes don't intersect those 2 planes. if they did intersect, they would intersect in a whole line in the x4 direction. But if I translate them a bit, then they won't intersect each other at all. Okay, on the other hand, the two green two planes do intersect each other. X1, X3 planes are transverse to X2, X4 planes. They intersect each other, and that's fine. Those intersections are these green crossings, which get mapped over there. Okay, so we have a green sort of two skeleton of a lattice and a blue sort of two skeleton of a lattice. They're interwoven with each other, so the vertices are paired off with nearby vertices. But because their directions are chosen in this clever way, the green is still disjoint from the blue, so that everything. So then we can map. We can have a map like this. So that is essentially the map that Sasha and Fedor constructed.
What about the force cell?
Yeah, okay, what about the force cell? So to finish the map, I have to map this junk here onto this force cell here. So there's a trick for doing that. The trick is that force cells are contractible. So there's a map from this thing to itself, which takes the force cell and sends it to a point. And this is a degree 1 map and a Lipschitz, I don't know, 10 map. And so if I start with the map in this picture, and it's a little hard to see how the white stuff is going to go to the force cell, but it will do that somehow, then I can compose it with that map, which smooshes the force cell so that whatever was going on in the stuff that was mapped to the force cell, then it got smushed to a point. So that part has Lipschitz constant 0. Yeah. Other questions or comments about this tricky map?
Yeah, fantastic. Yeah, beauty. It's incredibly beautiful. Yeah. This just mixture of classical topology and geometry. Just incredibly, yeah. It's absolutely breathtaking. Yeah, fantastic. Yeah. You agree, right?
I agree. That was well said. And this, let me say again, it's Sasha Berdnikov and Fedor Manin.
Yeah.
Okay. So,
and I just I wonder if it would have some really significant implications somewhere, for example, in physics. Yeah, it's really about 4-dimensional geometry, something very fundamental, which just is there. Yeah, it may have really profound understanding for our universe. I mean, it really looks very fundamental, very simple argument, but it's very, very kind of general nature, right? It's just how this kind of simple linear algebra incorporates into topology. And I think it looks to me very fundamental, something must resonate along many directions. Yeah, beautiful.
Yeah, we would love to hear about questions that somehow sound like they might be related. Okay, well, let me remind you that Sasha and Fedor proved that there was a map like this when k equals 2 that we just drew, and that there's a similar map when k is 3, but then not anymore when k is 4. So I wanted to try to give a sense of why that happens. So first I'll explain how do we modify our map when k is 3, and then what goes wrong when k is 4. Okay, so when k is 3, here's M3. It's a connect sum of 3 copies of S2 cross S2. I left out the yellow tubes from this drawing, but we have blue 2 spheres, green 2 spheres, and now purple 2 spheres. Okay, so we're going to do a similar thing. So we have this blue 2 skeleton of a lattice, which is interwoven with a green 2 skeleton of a lattice, which is interwoven with a purple 2 skeleton of the lattice. And when we set it up in coordinates, we have to decide what direction the blue, the green, and the purple go. So the blue and the green we do just like before. Blue, blue, green, green. And there are 2 other directions of coordinate planes that are left. So we make those purple. Okay, and just like before, the purple ones intersect each other. Any 2 planes of the same color intersect each other, and any 2 planes of different color are disjoint. So just for example, this purple x2, x3 plane will be disjoint from that one because they share an x2. It'll be disjoint from this one because they share an x3. It'll be disjoint from that one because they share an x3, and it'll be disjoint from that one because they share an x2. So that's what we do to go from 2 to 3. And what happens when we go from 3 to 4? Well, if I tried to add a fourth color to this picture, I would need to have some fourth direction of a two planes. And well, we're out of coordinate directions. So we can't have any more coordinate directions. Actually, you might try. Maybe I could have my, say, red two plane. It could repeat a direction. So maybe the red two plane also goes in the x2, x3 direction. But if we tried that, then it would intersect this purple plane in the x1, x4 direction. Or we could try having our two planes that are not coordinate planes. But it's not hard to check. If it's not a coordinate plane, it will intersect some of these. So there's nowhere to put more two planes that don't intersect the two planes that are already in this picture. Okay, so that's a hint of what goes wrong when k is 4, but of course it's not a proof. Basically what I said is that this one strategy for making maps breaks down when k is 4. And if the preimages are organized into flat two planes that are parallel to each other, then it wouldn't work anymore when k is 4. The degree would be a lot smaller. But of course, you might worry the preimages might not be organized into flat two planes and parallel two planes, and it could be something more complicated. So how do we rule out such a thing? Okay. So now we're talking about how to prove these upper bounds. All of the upper bounds are based on differential forms that represent the minimal model, as Misha mentioned earlier. And this proof uses the Whitney flat topology on forms and some like limits of forms in the Whitney flat topology. And this one uses Fourier analysis, which ends up being a little more quantitative than the limiting argument. Okay, so we have a map from mk to itself with some Lipschitz constant, and we pick out a bunch of differential forms alpha j that, if you know what this means, they make the Sullivan minimal model of M. If you don't know what it means, there's one form for each blue or yellow or green object in the picture that we had before. And in particular, so not all of these forms are closed, but some of them are closed, and they include generators of the cohomology of M. And so we can make the degree in terms of the pullbacks of these forms. Okay. So one thing we can do, say, classical approach, is we can estimate the norm of each of these forms in terms of the Lipschitz constant. And then we can use that to estimate this integral. And that gives L to the fourth. It's a different proof of the L to the fourth bound. But to do a little bit better than that, we can decompose each of these forms into a high frequency part and a low frequency part. And really, there's not just two frequencies. There's like a dyadic range of frequencies, like in Littlewood-Paley theory and harmonic analysis. So the high frequency pieces are good because a high frequency piece is rapidly oscillating. And when you integrate a rapidly oscillating thing, the oscillations cancel out. And so they don't actually affect this integral very much. And the low frequency pieces are good because low frequency differential forms.
It's frequency where? In pullback or before pullback? Where you,
in the pullback.
In the pullback, okay.
Yeah.
So it depends on degree, right? Frequency depending on degree.
I guess so.
So parameter here is degree, not the number of of terms, just degree. High, low with respect to degree.
Oh, high and low compared to what?
Degree or degree of the map.
Yes.
Yeah, okay. But the second parameter is the number of terms the connected sum.
The second parameter, the k?
Yeah, it's k, right? But this is not k, but this is parameter g. There are two parameters, in fact, here, right?
okay, maybe I make picture. So here is the domain. And it has a length scale 1. And then we take one of these pullback forms, F pullback of alpha, and we like break it up. You break it up like in Fourier analysis. So the lowest frequency part would have a wavelength around 1. So this is F pullback alpha frequency around 1. And the highest frequency part would have wavelength around 1 over L. So frequency around L. And there are also frequencies in between 1 and L. This L is the Lipschitz constant. Frequencies above that can be, they don't really matter. If we smooth out our map a little bit, there wouldn't be any frequencies that are higher than L. And these are the lowest frequencies here. So the high frequency pieces, they have all these oscillations. And when you integrate something that oscillates quickly like that, you get a lot of cancellation. So the high frequency pieces, they don't contribute that much to this integral. The low frequency pieces, if you look at a low frequency piece, then on a big portion of M, the form is basically constant. And what a constant differential form corresponds to is that it corresponds to the scenario where all of the blue planes are flat and parallel to each other, and so on for each color. So for a particular alpha would correspond to like the blue preimage, and a different alpha would correspond to the green. Maybe the horizontal blue preimage would be 1 alpha. And if this is a low frequency piece, so the differential form is basically constant, it means that when we look here, we see parallel flat planes. So once we're down to the low frequency piece, we're in that special case where we can use that kind of linear algebra argument, where basically we say there's nowhere to put the fourth color planes. This is not a full proof. This is a sketchy thing to try to give a flavor of the proof.
But instead of differential forms, right, you can look at the pattern of intersection, right? And the same Fourier analysis would apply in some sense. And then geometrically you can feed the two pictures. Right, when they have this high frequency, they become very twisted, and so they intersect 2 ways and cancel each other. That's the idea, right? These very twisted pullbacks may intersect each other in opposite direction many times and cancel off intersection numbers, right?
Yeah, correct. That's the idea. Yeah, let me draw what Misha is saying. So, okay, so here is our target. And then over here is just one of the blue pieces. And there's a form alpha, which is the Poincare dual to the core 2-sphere. And it lives on this blue piece. Okay, so in the example the old example, what we saw was that the pullback here looked like this. And that corresponds to that the pullback of this form is low frequency, essentially low frequency. And then what would it look like if the pullback of the form had a high frequency piece? It would be a new example. And it's just how Misha described that each one of these, instead of being flat, is all twisted. Something like this. Okay, so that corresponds to the pullback of alpha is high frequency. So what's the difference? The pullback of alpha, it knows the tangent direction here, and it knows like a co-orientation. So here the co-orientation is always the same and the tangent direction is always the same. But here when this thing turns around, the co-orientation here is the negative of the co-orientation there. And that corresponds to the differential form being, say, positive dx1, dx2 here and negative dx1, dx2 there, and oscillating positive, negative, positive, negative, positive, negative, positive, negative. So the high frequency part, having a high frequency form means the preimage is all twisted like that. And that helps us, just as Misha said, because if you imagine how this thing intersects, I guess it would also be, my original color coding would also be blue, but it will be clearer in our discussion if I make that green. So now we pull back a form, maybe beta, that lives here to do our degree integral. So that pullback looks maybe like that. And then the intersections cancel. There's, say, positive intersection, negative intersection, positive intersection, negative intersection. And that cancellation gives us the gain in the degree. Yeah, that's right. That's right. And that's a beautiful picture. And I think Misha is suggesting it might be nice if we wrote the whole proof in terms of this picture instead of in terms of this more opaque Fourier analysis.
Something else what reminds me of. If you think about self-avoiding random walk in dimension 3, and then there are, I think, similar phenomena may happen. So, and these can be used for this kind of stuff. Yeah, you look at the random surfaces in 4 space, or maybe even 3 space, and how this thing cancel. We have Fourier analysis. On one hand, there is topology, which forces intersection, and then there's some cancellation due to oscillation. And there may be really new approach to this kind of mathematics. Or also my high dimensional percolation. Again, percolation not for curves, percolation on the surface level. And of course, the most fascinating classical problem is understanding self-avoiding random walk in dimension 3. When you see there's maybe self-notching of curves, and so in principle, you can imagine that there is even no statistic. There may be really very different kind of patterns depending on the topological self-notching of these random walks. So you can imagine that really the spectrum in this probability. But this kind of very powerful ideas, they must have tremendously many applications. That's what you say, both first and the second, is incredible. It's extremely simple and basic ideas involved. And just, I just feel really kind of very excited. It must go very, very far. Yeah. I knew about the result, but I never followed the proof. Yeah, you explain them so clearly. It's fantastic. Absolutely. I attract attention to everybody. There seems to be new domain in mathematics opening with many applications. Yeah, clearly. Yeah, it's very, very beautiful. Yeah, I could never imagine it would go so nicely. I mean, absolutely beyond the imaginations. Yeah.
What are some of the questions about self-avoiding random walk in 3 dimensions then?
How far it goes. It's unclear whether it goes faster or slower than the square root of the number of steps. And I would think it's slightly different term. You look at the space of all random walks and the space of this self-embedded curves, etc. It's extremely complicated space. You have a really thick kind of tube dimension space. You have a tube with some thickness, and how it can be twisted in the space to fit and what shape it would have, right? It's very complicated, and so probability measure sits on this very, very strange space. It's kind of have very similar in spirit. You cut away intersection point and these kind of diagonals in this space. So it's like this linear algebra pattern. You cut away these pieces, and what remains, and the measure leaves on this very kind of ugly space. And so this very fine mixture of topology and probability and probably Fourier analysis enters. Right? Maybe also some kind of scaling. People, of course, all the time try to understand scaling, but they never think about topology seriously because they are probabilistically minded people. On the other hand, knots, I know, studied and studied by people who are using RNA and how RNA knot in this space. They make actually experiment how it knots and why it's a knot and what it makes. It's another kind of domain. It's not so famous, but also very interesting. What makes your DNA and RNA are knotted despite the symmetry of notching and unnotching. Of course, there is some enzyme which contribute to free energy, but it's still very kind of remarkable that this phenomena happened. And of course, this level of ideas was never there. I mean, people think in much more simple terms. If you bring this idea there, it may really turn the tide in a new direction. Maybe, maybe not, of course. Dimension 2, of course, also self-avoiding random walk, we don't know. It was bigger square root of 2 or less than square root of 2. It's incredible, we don't know this year. And so, and you know that in physics, this was done by Flory, and it really, he understood this excluded volume and explained very many phenomena, very roughly. Computationally, still it's unclear what happens. Yeah. Why molecules behave in this or that way when they're long molecules. But it's only excluded volume, only kind of the tube has certain volume, and so you cannot occupy the place with not enough volume. But topology tells you something else. And so it may give completely new kind of evaluation of this. But nothing is known, non-trivial for how big displacement is. There are kind of there are some theorems, but they're kind of peanuts, and infinitely far from what is known. So it's a fantastically kind of challenging field. It looked always very ugly and unclear what to do, but this suggests really conceptual approach to it. Maybe, maybe not. But if not to that, but to something parallel to this theory, I would say.